my name is Tommy, and today we're talking about periodic trends. So, for this, we have to draw an arrow representing the following periodic trends: atomic radius, ionization energy, and electronegativity, and electron affinity. So first, atomic radius. So, let's think about this in terms of Coulomb's law, where the more force we have attracting an electron, obviously the closer it's probably going to be to the nucleus. So when we go down a group and we're adding energy levels, it's like we're adding floors of a building. So the thing is going to get weaker and weaker, or the atomic radius is going to get larger and larger. So atomic radius will increase as we go down the periodic table. Now if we go across the periodic table, or to the right of the periodic table, atomic radius will decrease because as more protons are added, they're going to attract those outer electrons more and more and more, bringing them in. So in total, our atomic radius arrow is going to look a lot like this, going down from helium all the way to francium, which is down here. Our next one, electronegativity, which I'm going to use green for, or not electronegativity, ionization energy. Ionization energy, which I'm going to use pink for. Ionization energy is how hard it is to take away an electron from an atom. And the way we can do this is by thinking about it with Coulomb's law again. The closer it is to the atom, the harder it is to take away from it. So, ionization energy is going to go opposite of atomic radius, because the smaller the atom, the harder it is to take that electron away. So it'll go from francium to helium. Now the next trend is electronegativity, which will be represented with green. And it's basically if in a compound, how much is this element willing to share, or is going to try and take those electrons for themselves. So you can link this with atomic radius by, if it's smaller, it's going to be closer to those electrons and try and grab them more. So it is also going to run opposite of atomic radius. Except, actually, I'm going to cut it short to here, because electronegativity does not really extend to the noble gases, because noble gases do not bond and share electrons with other elements as much. For electron affinity, usually it's about how much energy is gained from an electron. So if for nonmetals, the gain is usually negative because they're receiving that electron. And for metals, the gain is usually positive because they're losing that electron. So what happens, since most of our nonmetals are over here, and most of our metals are over here, is we'll see an increase from helium to radium or actinium, to that kind of range. So, with the exception that these over here are mostly pretty positive. But other than that, that is how, in general, electron affinity works. For this problem, we need to look at the differences between Mg and Sr. Specifically, which is smaller, more electronegative, and has a lower ionization energy. So first of all, an atom is smaller on the periodic table if it is to the top right, and larger if it's to the bottom left. So for this case, since they're both in the same position on the x-axis, on the y they are different. So looking at it like this, we can see that Mg is smaller because it has less energy levels than strontium. So our smaller would be Mg. For electronegativity, remember, it follows the smaller atom. The smaller the atom, the more electronegative it is. So using that logic, we can say that Mg is again the atom of choice. Now for lower ionization energy, what we're looking for is that the electrons are easier to remove. And for that, you want more outer levels, or the electron to be farther away from the nucleus. So for that, in that case, we're looking for the larger atom, which in this case is strontium, due to its extra energy levels compared to magnesium.